we're studying 4 of the what are reckoned to be most important equations in physics, called the Maxwell equations. This is a little overhead of a new scientist from a couple of years ago. And it says 7 equations that changed the world. And 4 of these 7 equations are the Maxwell equations. And of course you're studying the Schrödinger equation, and the laws of thermodynamics are also massively important, and you'll be studying next year. So we're up to now this stage of being able to take these on. And in particular, the reason that you might think, well, you know, why on earth did I do Electromagnetism 1 and study this without studying the Maxwell equations? Well, your maths wasn't up to it at that point, because you'd not studied Gauss's theorem and you've not studied Stokes' theorem. And until you've done vector integral calculus, you can't appreciate what the Maxwell equations are all about. However, you are now at the stage where you can do exactly that. The reason, one of the many reasons the Maxwell equations are important, is that as far as we know, they're true. And so this is the first time you'll have been exposed to the true equations of physics. Even the Schrödinger equation, which isn't relativistically invariant, it's only an approximation to the Dirac equation, which you might study if you're doing, you know, the 4th year MPhys course, which is quite a difficult piece of work indeed. But these 4 equations were developed in 1861 by Maxwell. And here again, this is a very old new scientist. This is from 1999. And this one is saying the Maxwell equations are part of the theory of everything. So you can see here, before 1861, electricity, magnetism, and optics were separate subjects. However, after Maxwell's unification theory, this brilliant piece of work that we're going to study this term, we had one single subject, electromagnetism. Now, electromagnetism, that is where I'll be taking you this term. I'll also mention a little bit in a slightly more advanced lecture where I'll just hint at what the unification between electromagnetism and the weak interaction is the so-called gauge theory, and give you an idea of how electro-weak theory has been obtained. Of course, that will not take you the whole way. The strong interaction, responsible for holding the nuclei together, which is described by quantum chromodynamics, is way beyond what we're going to do. And the grand unified theory, where you unify the strong interaction with the electro-weak, is as far as we've got in physics. Nobody has succeeded in unifying these 3 forces of nature with the 4th one, gravity. Toes are, you know, well, they are the things on the end of your foot, but in this circumstance, theory of everything, toes, we might, perhaps it's string theory, we don't know. There are still people working on this. However, you're certainly not going to understand this massive picture unless you can understand this first unification theory. And that's, as I say, where we're going this term. Now, indeed, the unification theory, one can date actually to a particular day. In fact, the 19th of October 1861. And if you look on the inside cover, obviously the main thing for the handout is that there is a load of diagrams in the handout. The main idea is to save time so that we've got figures and figure numbers that we can refer to, you know, very much like I did with Maths 1. So the main idea is, of course, so you've got lots of convenient diagrams, so I can just slap them down. You can either make notes on these as we go along, or, you know, use them in whatever way you like. They do make, you know, excellent paper gliders and so on. So you can see that the inside cover, there was an odd number of pages, so I thought, well, I might as well use one of them in hopefully an inspirational way. And this is the letter that James Clerk Maxwell wrote to Michael Faraday on the 19th of October 1861, From the determination by Kohlrausch and Weber of the numerical relation between the statical and magnetic effects of electricity, this is what we now call epsilon naught and mu naught, weren't called that in this period, but that's what he means. I have determined the elasticity of the medium, and assuming it is the same with the luminiferous ether. Now again, the ether, the luminiferous ether, is a concept that has fallen away, but since Einstein's work, but nevertheless Maxwell used it in his thinking. I have determined the velocity of propagation of the transverse vibrations. The result is 193,088 miles per second. He then comments, Fizeau, this is a very brilliant piece of experimental work, has determined the velocity of light to be 193,118 miles per second by direct experiment. And then the line which any physicist would have kind of like almost literally given their right arm to be able to write down, this coincidence is not merely numerical. So by studying the known laws of electricity and magnetism, Maxwell derived that he called them transverse vibrations, we now call them electromagnetic waves, must travel at the speed of light. And this completely revolutionized physics. Sometimes people exaggerate, but there is no exaggeration at this point. This was the greatest revolutionary moment in the history of physics, the first great unification theory. So I took that page from this book, and I know you're incredibly busy people all through term, and you don't have time to go back to the original letters and papers of James Clerk Maxwell, but I just thought I'd give you a little bit of the idea of his life. You know, in this lecture we're not going to cover much of the actual physics. We're going to take a kind of overview of the Maxwell equations, and we'll start the real nitty-gritty physics tomorrow, though we will make a bit of a start on that today. So you'll see that the volume is dated from 1846 to 1862. Well, Maxwell was born in 1831. So you can see he was incredibly young when he had his first published paper. Around the time most of us were taking GCSEs, he made some revolutionary advances in pure mathematics. So this paper, which he produced in February 1846, and so he was at this point 14 years old. Observations on circumscribed figures having a plurality of foci and radii of various proportions. He was the first person to really solve what are called the oval curves. So this was one of the greatest advances in Cartesian geometry, or if you like, analytical geometry, that had been made for 2 centuries. And he made this advance when he was 14. The sort of background to it is his father took him to an exhibition and these very beautiful ovals. And he'd learnt a bit in school about how to write the equation of a circle. And he sort of said to his dad, after the exhibition, he came home, jotted a few notes down, and said, Dad, is this the equation for those interesting ovals? And his father kind of, well, not sure about that, and sent it off to the professor in Edinburgh. He was born and brought up in Edinburgh. Then the professor, a few weeks later, wrote back to his father and said, yeah, not only I've checked these, not only are they true, they're completely new and original. So, of course, we're dealing with the work of a first-rank genius. When he was 14, he solved oval curves. So, obviously, he was going to go to university. He applied to York and didn't get in. Fortunately, he sneaked into Cambridge on clearing. And this is, he went to Cambridge in the summer of 1848. This is around the time of his 17th birthday. He then solved what are called the rolling curves, in which one curve rolls on another. So, you know, for example, if you have a speck of dust on your bike wheel and the bike's travelling along, you have a circular motion transposed onto a uniform translation, and the motion we now know is what's called a cycloid. And in fact, you might have studied that with Kieran in first year electromagnetism last year, that the cycloid is the motion of a charged particle in crossed electric and magnetic fields. You may or may not remember that, but or I'm not sure if Kieran covered that when he did motion of charged particles in electric and magnetic fields. But this so-called cycloid curve was one again that was solved for the first time by Maxwell. So you can see we're dealing with an amazing man whose mathematics was extremely advanced. Fortunately for us, he was born in the era before maths and physics diverged, and the greatest physicists in the world were also the greatest mathematicians. Indeed, the word physicist didn't even exist. He was professor of natural philosophy, so-called, at the University of Aberdeen. That was his first job. And I kid you not, there were 2 universities in Aberdeen at the time Maxwell was professor. And in 1860, he became a full professor when he was about 24. You imagine that people these days are still, writing up their PhD theses. He was already the professor of natural philosophy. And the 2 colleges in Aberdeen were amalgamated into one. And in the new college, there was only room for 1 professor of natural philosophy. And they sacked Maxwell. Yeah, I kid you not. And in fact, he had perhaps as a result, he had a nervous breakdown, and in the spring of 1861 was extremely ill. And it was when he recovered that he did the incredible work that we're going to study. Here's a picture of him at Cambridge in the autumn of 1855. I think this is the first known photograph of him. And just to mention here, he's holding a colour top. And a load of things that we take for granted now, like the three colour theory of vision, that you can make any visual combination from green, red and blue, pure light, was Maxwell's. His whole theory of colour vision was Maxwell's. He did amazing things. There was a prize offered by the Royal Society to find out whether the rings of Saturn were liquid or lots of little bits of rock, and he proved from first principle classical mechanics that they could not be liquid, that they had to be individual pieces of rock, that a circulating liquid in this way would not be stable. He founded, along with Boltzmann, the whole subject of statistical mechanics that you'll study in year 3. And in fact, one of the reasons, like in the general public, everybody's probably heard of Newton and Einstein. In 1999, at the end, there was the greatest this of the millennium, the greatest that of the millennium. And one of the things that the Institute of Physics did was they asked members to vote for who was the greatest physicist of the millennium, and it was almost a 3-way tie at the front between Newton, Maxwell and Einstein. Personally, I think he was the greatest of them all, and to say that a scientist was greater than Newton and Einstein is not something you do lightly. Now, Maxwell did write his own book on this is a picture taken of him at a later stage. Looks a bit like Plato, massive beard, looking very impressive. But this is a very difficult book. I only say, this is for the sake of completeness. And in particular, Maxwell used the quaternions, which were invented by Hamilton in 1844 to express his equations. We now use vectors, or indeed, as we'll come on to perhaps towards the end of the course, tensors. Although for our examination course, we'll only use the vector notation. So it's a very difficult book, and it's worth looking at because if only to look at the first 2 or 3 pages and the way it exudes confidence. He starts off by talking about all the great advances that have been made in Germany by people like Weber and Gauss and so on in electricity and magnetism, and then just full stop. This, however, is entirely alien to my way of conceiving the phenomena, and off he goes. And in particular, he abolished action at a distance and developed what we now call field theories, which dominate the whole of modern physics. However, his own book is quite hard. There's no 2 ways about it. And the book that I recommend in particular, sorry, this is a bit grainy, is the Feynman lectures on physics. And I've based my lectures unashamedly on those. This is volume 2, mainly electromagnetism and matter. And, if you're doing a series of lectures, kind of making a copy of what's probably the greatest lecturer of all time is not a bad thing to do. And indeed, if you go to the VLE site, you'll find references to the Feynman lectures. There are particular chapters that are very important for the course. So please do look at the Feynman lectures. The Feynman lectures are more full and they are more difficult than my course. My course is bringing out the essential features of these lectures. Feynman lectures will go on to a much higher level. If you want to go to a very high level in physics, read the whole lot. Now, one of the reasons that I chose Feynman is not just because he was renowned as a great lecturer, but he won the 1965 Nobel Prize in Physics was awarded to Feynman, Schwinger and Tominaga, quote, for their development of the theory of quantum electrodynamics. So you can imagine that the man, one of the three men, who won the Nobel Prize for developing quantum electrodynamics understood classical theory. I mean, if you like, a century after Feynman, after Maxwell, electromagnetism, we get QED, quantum electrodynamics was more the 1960s. There was a century of development before you get from that step to that step. And you can imagine that the men who developed quantum electrodynamics understood classical electrodynamics very well. My course is purely classical. We're not going to deal even with the graininess of charge. Charge is going to be a continuous variable. You need to get to a higher level in quantum mechanics as well before you can appreciate quantum electrodynamics. So Feynman understood electromagnetism at a very high level, and that is expressed in his lectures. So the next thing is a picture of Tominaga. This is completely irrelevant to the entire course, and I just thought it was a really cool photo. So. Irrelevant jokes. Oh, by the way, the jokes have changed this year. Only very slightly, because I've only got a repertoire of about 3 or 4 jokes, as you know. But I've moved on from biology jokes. Instead, we've got psychology jokes. This is in honour of our new Vice-Chancellor, who's a professor of psychology. So another good reason for having the lectures recorded is I'll probably get fired in the middle of term. And at least you'll have something to work on after that. Again, I repeat, I don't want to give the impression that I don't like psychology. Same joke as last year, it's just that I prefer science. I'll be fired before Wednesday at this rate. I really should. No, okay. So anyway, it's time for me to stop waffling aimlessly about the generalities. And I know actually it's different. Some people like the historical background, some don't. I've been trying to, motivate the course a little bit in the last 20 minutes or so. So I just want to run you very briefly through the outline. There's the Maxwell equations, and now I'm going to do electrostatics really in one lecture because you did so much of that with Professor Gibson last year that I really don't want to retread the same ground. And in fact, there's nothing on my exam syllabus at all on electrostatics, but it's good, it's a good way to get back into the electromagnetism because it's the easiest part, not because it's the most interesting, far from it, but it's certainly the easiest part. So we'll have a look at that. Again, I know you've done steady state magnetism before, but lectures 3 to 6 will be on that, steady currents, using Ampere's law, the Biot-Savart law. Because your maths is now a lot better, you'll be able to understand that, and in particular I'll introduce a new concept called the vector potential, which is a very beautiful way of handling steady state magnetism. We're then going to go on for a week to Faraday's law, and then something that will be, again, you've studied that in a qualitative way with Kieran, but I'll be doing that rigorously this year. And then the Ampere-Maxwell law, which will be completely new to you. And then I'm going to do the unification theory in about lecture 11 and 12. My philosophy is that I'm going to go up the steep side to 29,000 feet so that we'll get to the top and be able to see the whole view by early February. It won't be easy. And obviously I think I can show you a good way to get to the summit, but you have to be prepared to do the intellectual climbing. You know, you have to be prepared to do quite a lot of work to get on top of this course. It won't come easy, but it's worth it because the view from the top is great. Once we've got the view from the top, I'm going to do optics. The optics part of the course will be then the next sort of roughly 9 lectures up to about lecture 20 or 21. And then I'm going to look at the topic of energy, which unifies, as it does in many areas of physics, different areas of magnetism, electromagnetism and optics. And then next term, in the summer term, I'm going to be doing the properties of materials. Electrical and magnetic properties of materials, I mean. So if you like, the really steep part and where I hope you're really going to concentrate, in the next 4 weeks, by the middle of term, we're going to do this 80. You should be able to understand everything about how Maxwell did this unification. And then a more traditional course often puts the Maxwell equations kind of at the end. You know, you build up gradually step by step, but then you don't get the advantage particularly of looking at optics. Optics becomes actually a much easier subject once you've already understood the Maxwell equations. So that's the philosophy of the course. Now, it's all very well doing all this stuff, but what are the Maxwell equations? So let's start off. It would say, I think a good place to start this course would be to write them down, and that's exactly what I'm going to do. Now, one of the things that all the lecturers are asked to do, and I hope everybody does this with some clarity, is to say to you, how do I get a good set of notes from this course? Well, available on the VLE are complete lecture notes and also summaries of all the lectures. However, those lecture notes are actually more than you need. They contain some additional material. As I go through the course, I'll be pointing, there's also various advanced topics on the VLE. So there's going to be less in the lectures than there is on the VLE. There's not a one-to-one mapping between what I'm going to do in the lectures and what's on the VLE. That's deliberate. They push a little bit further. They're sort of halfway between my course and the Feynman lectures. So, however, I can tell you that if I write it on the board, it's definitely important. You have, there's the stuff already on the VLE. So there's no point me writing, you know, standing blah, 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 and then, you know, you can see it on the VLE anyway. So sometimes I'll simply refer to lecture notes on the VLE. And there's not only complete lecture notes, but there's summaries of each lecture too. So there's loads of backup there. And there's also, hopefully, if things are going well, recordings of the lectures as well. So I'm going to start off by writing down the Maxwell equations because that is obviously so important that we can't get away from it. So here we go. Lecture 1 is the Maxwell equations. And the four Maxwell... First of all, I'm going to say, and again, this one is identical to what's on the VLE notes, all of electromagnetism is contained in the Maxwell equations. This is one of the many reasons why they are so important. Again, you probably got used to this last year when I did Maths 1. Equations is a word that we use so often. I'm just going to abbreviate it EQ and then NS. So all of electromagnetism is contained in the Maxwell equations. And the first one is for the divergence of the electric field, which is equal to the charge density. This is a Greek rho over epsilon naught. I'll define, of course, all of the variables below as well. this, of course, is the permittivity of free space. So this one is the first Maxwell equation. And again, just like I did in the Maths 1, I'm going to label the equations because I think that's good, because then I can refer back to and forwards to equations with the one. In other words, this is equation 1 of lecture 1. So that's the first Maxwell equation. The second Maxwell equation is the other equation for the electric field, and it states that the curl of the electric field is equal to the negative rate of change of the magnetic field. So let's make that equation 1, 2. So there are two equations for the electric field. They are the divergence and curl. And again, this is precisely why, you know, we study this course after you've done the Maths 2 course, because you've got to know what divergence and curl mean to appreciate the content of the Maxwell equations. So the third is for the divergence of the magnetic field, which is equal always to 0. And the final Maxwell equation, this is called the Ampere-Maxwell law, is for the curl of the magnetic field, and this is equal to mu naught, which is the permeability of free space, times J, which is the current density. I'll come back to that in a minute. Kieran used current I, and most people in elementary electromagnetism use a scalar current, but this J is much more general because this doesn't have to be like confined to a wire. This is the number of amps flowing per square metre, or if you like, the number of coulombs per square metre per second through any infinitesimal area element. And this is a much better way of dealing in general with charges in motion than to talk about currents. So this is a vector quantity. And then the next term was, this was discovered purely theoretically by Maxwell. This is why this, as I'll show towards the end of this week and next week, this is equivalent. You don't see it probably immediately from what you did last year, but this is equivalent to Ampere's law. And Maxwell realised that Ampere's law couldn't be generally true, and he discovered that this term would have to exist. This is mu naught epsilon naught times the rate of change of the electric field, and we'll make that equation 1, 4. So where, obviously, all physics equations are meaningless if you don't say what the variables are. Rho is the charge density, and the charge density is in coulombs per cubic metre. Now, as I said, I am not going to deal with quantization of charge at all in this course. I'm not saying this course, you know, it will give you the unification theory, and it will take you to where physics had got to in 1861. It won't deal with quantization of charge. So we'll be looking at the approximation in which the charge is smeared out. I'm assuming that the charge density is a continuous function of the three variables x, y, and z, and that this is in any local infinitesimal volume around that point. I can define how many coulombs there are per cubic metre at that point in space. So this is a scalar field. Oh, wrong way. So rho is the charge density, J is the current density, and this is in amps per square metre. So again, you know, just a little scribble in the corner here. If we've got some little infinitesimal area element in space, J is the number of amps per square metre flowing through this infinitesimal area. Again, this is a classical field theory. I'm assuming this can take any value. we've not got discrete lumps of electrons flowing. We've got a charge which is a continuous variable and a current density that's a continuous variable. The remaining symbols, well, epsilon naught is the permittivity of free space. This one is usually written in farads per meter. Again, I'm going to come back to the units in electromagnetism after we've done the unification theory. It's actually easier to understand why all the units are the way they are when you've seen the whole picture. So at the moment, I just ask you take it for granted that these are, the right way of writing all the units, and we'll, as I say, we'll revisit precisely that problem at the end. So let's just move these up a bit. Mu naught is the permeability of free space. And this is usually written in terms of henries per meter. Henry was actually the surname of an American scientist who did a lot of work in magnetism. So that's henries per meter. Del is the operator. Again, the vector operator that you will now be very familiar with, d by dx, d by dy, d by dz. Or like again we did in maths last year, I could write this as I hat d by dx plus j hat d by dy plus k hat d by dz, where I, j and k are unit vectors in x, y and z directions. And this has units of meters to the -1. It's funny actually, very early to think about examinations, and we'll put thinking about that off till the summer term in general. But for all of the last 3 years that I've taken the course, one of the questions, the threshold material, 6 or 7 marks have been write down the Maxwell, I'll give the Maxwell equations and say, incredibly easy question, what are the meaning of all the variables in it and what are their units? And amazing numbers of people make the mistake of saying that del has got no units. Oh, that's mathematical. Well, I haven't got any units because it's a mathematical thing. No, it's per meter. In fact, just think, again, I'll come to this in a bit more detail in the electrostatics, but E is minus del phi, where this is the electric field and this is the electric potential, and this is in volts per meter and this is in volts. An electric potential in volts, an electric field in volts per meter, so this operator had better be in per meter, and of course it is. So this, it's not a well, it is a mathematical thing, but it's certainly also got units. So that's the operator, and then last but not least, we've got to define the two fields. E is the electric field, which, as I've just said, is in volts per meter, and B is the magnetic field, and this has the SI units of Tesla. So we've done the absolute basics. These are the 4 Maxwell equations and what all the symbols involved are. Now you can see that there are 2 equations for the electric field and 2 for the magnetic field. Now, what we're going to start off with, again, I'll make a board note on this in a minute, and it's crucial to recognise that these 4 equations, as far as we know, of course somebody could do an experiment and find out that one or all of the Maxwell equations were wrong. But a lot of experiments have been done since 1861 and nobody has yet found an experiment which contradicts them. Usually, every few years there's a challenge to del dot B is naught. And what that equation is telling us is that there's no such thing as a magnetic monopole. there's no possibility of having a magnetic field that diverges from a point. And almost every time there's incredible excitement for a few months, and then people repeat or reinterpret the experiments and they realise, no, there's actually no magnetic monopoles. Of course, we've been perfectly entitled to challenge these equations. We don't have, I mean, Newton's laws stood for over 200 years before Einstein's work in 1905 from the Principia in 1687. Just because nobody's found that the Maxwell equations are wrong in 153 years doesn't mean that, tomorrow somebody might do an experiment and find out that they are wrong. However, as far as we know, they're right. So as written in that way, they are definitely absolutely true as far as we know. However, the way that we're going to study them, and the way most people always do it, is to start with what are called the static fields, because they're easier to understand. And in particular, if the rate, in a sense, there's no such thing as magnetism that's static. That's what del dot B equals 0 is telling us. But there's a specific case if you've got a large number of charges in steady motion, for example, just a current flowing round a circuit. We've got a battery and a piece of wire, not a very difficult experiment, and current is flowing around the circuit. That is a steady state. That's not when the battery's just been switched on or we switch it off and the current changes as a function of time. This is a completely steady situation that's described by this current density J when it's time independent. And in those circumstances, if rho is also constant and J is constant, in other words, charges aren't moving or are moving in a completely steady way, then the fields don't change with time. And in those circumstances, saying that the magnetic field does not change as a function of time, well, clearly then the curl of the electric field just becomes 0 in the case where the magnetic field is static. Likewise, if the electric field is static, this term disappears. So in these circumstances, this refers ahead to lecture 11, is that this equation here is often rewritten. When you've done the unification theory, you can eliminate mu naught. We'll of course be coming to that. But whichever way you look at it, if the fields aren't changing as a function of time, then the two equations for the electric field are these two, and the two equations for the magnetic field are these two, and it appears that they're completely separate subjects. So if we don't have dynamic fields, and this is precisely why electricity and magnetism were discovered separately and were regarded as separate subjects. And if again, this is not obvious to you that at the moment, but I'll prove it in the lecture tomorrow, this is the same as Coulomb's law. Doesn't look much like Coulomb's law in this form, but it is Coulomb's law. And this is the law, and it's important to realise from the outset, Coulomb's law is emphatically not a true law of physics. It's a static approximation to the electric field. And what it does is it says that the electric field is entirely determined by where the charges are, the charge density. And that's what is also contained in Coulomb's law. Likewise, when the electric field is not changing as a function of time, it appears that the only variable that determines the magnetic field is the current density. And again, this doesn't look much, those two equations probably don't look like Ampere's law to you, but in lectures 3, 4, 5, 6, we'll be discussing that. So this is a very, very beautiful setup, and we're going to start with this because this is what we get familiar with. This is a good old familiar, back to the safety zone of potentials, and indeed, this is precisely, we can only define an electric potential when we have a field that has no curl. Again, I hope you studied that kind of idea with your Maths 2 course last term. And just to emphasise, because we get so used to it, and that we can define a gravitational potential. A Newtonian gravitation is also, like Coulomb's law, an inverse square field. We get used to that, we can define a gravitational potential, and so on. I want to emphasise right at the outset that there is no possibility, it is absolutely impossible to write that the magnetic field is the gradient of some scalar field. It isn't. Can't be written down. Again, I'll prove that in the lectures next week. But it's certainly a completely different kind of animal. And that's why, you know, we lead to studying it to the second year, because it's a more difficult field to deal with. So that is the setup, the way we're going to go about things. So I know you've already done it in maths, but I just want to make a very quick note on precisely the divergence and curl. So this is a 2-minute revision of the whole of last term's course, basically, in maths. The divergence and curl, and this, well, the Maxwell equations are written in terms of these operations. So we've certainly got to understand them. And I'm going to use this too. As I say, I'm setting things up today. When I use vector calculus, which is generally true, I'm going to use C as that vector field. And of course, if something is true for any vector field C, it will certainly be true for the electric and magnetic fields by virtue of the fact that they're vector fields. So I'm going to use C for a general vector field, are defined by, and del dot C, again, I hope everybody who is on the course is completely happy that I'm about to write down dcx by dx plus dcy by dy plus dcz by dz. And this I'll make equation 1,5. So that's the definition of the divergence of the field. And of course, the most important thing to note, it's a scalar. Anybody writing down that the divergence is dcx by dx, comma, dcy by dy, comma, and dcz by dz, close brackets, immediately shot. Not very PC for lecturers to shoot students these days, but you know, I feel I have to do it in the circumstances. So please, this is a scalar. Or alternatively, look at equation 1,1. I mean, what's the right-hand side of it? It's a scalar, the charge density. It's not a charge density, it doesn't have a direction. It's 3 coulombs per cubic metre in that direction and 7 in that, does it? It's a number. So of course, this is just a number. So this is the divergence, and that the curl is equal to the vector defined by this determinant. Let's make that equation 1,6. So, of course, again, look at the right-hand side of equation 1,4. Let's just look at the first term. The current density is a vector. That does have direction. I can have a current flowing in that direction, and a current flowing in that direction, and a current flowing there, and a current flowing there. This is a vector quantity, so this is the correct derivation. And just qualitatively, again, just to get the feel of it, the divergence at a point. I know some of you are more brilliant at maths than others. Some people are better at intuition than others. And I think for a physicist, it's really important to be looking at it in both ways, to have a feeling for what the symbols mean, as well as being able to manipulate them. So even if you're good at maths, don't just poo-poo, you know, the trying to describe things in words, because in the end, nature's so complicated. A lot of the time, we can't solve the Maxwell equations exactly. There are only certain very highly symmetrical problems that we can actually solve outright with maths, but there are lots of things in nature that we would like to be able to study where we can't solve the equations, and then having a feeling for what they're telling us is definitely important. So the divergence at a point tells us what flux of the field originates there. So it's kind of source from which things spread out. That's what the divergence is telling us. It really, it's the word. It's diverging. It's diverging from a point. It's something spreading out. It's flux spreading out from a point. Similarly, the curl, again in a very qualitative, crude way. What's the curl at a point telling us? The curl at a point tells us what circulation there is about that point. Again, I know probably by middle of the year, student loans have all run out and you can't afford to have baths these days, maybe only a shower or something. But every time, like you let water down a plug hole, you see it swirling round and round, and it's got a circulation, and that's obviously a field with a non-zero curl. So don't be afraid to use some of these more qualitative interpretations rather than the pure maths. So again, what I'm going to finish up with is now just leading up to, and it's so important, although it's up on the view graph, I want to re-emphasise it. So when rho and j are static, are constant, excuse me. J is obviously a flow of charge, so I shouldn't call it static. When rho and j are constant and the fields are static, in other words, dE by dt and dB by dt are naught. So rho and j are constant and the fields are static. The Maxwell equations become, this is del dot E is rho over epsilon naught. That doesn't change because it doesn't involve a rate of change of the field, and del cross E now becomes equal to 0. When dB by dt is naught, we have a curl of an electric field equal to 0, and, well again, this never changes. The magnetic field never has any divergence, and the second of the laws for the magnetic field, equation 1,4, we drop the second term, and this just becomes equal to mu naught j. And to say that in words, the Maxwell equations split into two pairs. We'll see that all of the really interesting stuff in electromagnetism, the interesting stuff is in the dynamic fields, and the unification theory, of course, is in dynamic fields. We're going to look at transverse waves of electricity and magnetism. So the interesting stuff is the dynamic fields, but it's much better to start with the static fields because they're easier to understand. So the Maxwell equations split into two pairs. One for electrostatics, and one for, it's a strange word this, magnetostatics. Feynman calls it magnetostatics, and he wasn't too bad at electromagnetism, so I don't feel too bad about using that. But it can mislead you. In one sense, there's no such thing as a static magnetic situation, because charges have to move in order to make a magnetic field. But it's when they're moving steadily that we get this particular kind of approximation. And you can see from a maths point of view, these are really, really beautiful, because here we've got a field with finite divergence and zero curl, and the magnetostatic situation is exactly the opposite. We've got a field with zero divergence and finite curl. And as I mentioned, this pair is equivalent to Gauss's flux law of electrostatics and therefore to Coulomb's law. Something that I will prove to you on Wednesday. Okay, it's great to see you all again. Could you, by the way, if you find any spare handouts, return them, because there might be people who are not here today who need them. And also, if you need a handout, there's a few spare at the front. Okay.